Okay, example 6 in this equilibrium section again comes without a diagram, so it's going to be the first thing we do. There's got this key line, it rests in limiting equilibrium. So just like we said in the previous example, this tells me that friction must be equal to mu r if it's at limiting equilibrium. And it's an inclined plane, 20 degrees to the horizontal. So let's draw that out. Here's our incline, 20 degrees. We've got an object, it's 10 kilograms at rest. And so we must have a weight pulling it down of 10g. And it says there's no other forces, right? So if it wasn't for friction, what would happen when we put this box on here? Well, it would slide down the slope, wouldn't it? Right, because this 10g is pulling it down the slope. But obviously there is a frictional force which is opposing it. And we know because it's in limiting equilibrium, this will be equal to mu r. We can also put in the reaction. We're going to need it. We can put in that this is 70, right? Because we know the 20, 70 and 90 will make a triangle. And we can just mark in the diagonal there for clarity. So find the coefficient of friction between the box and the plane. So to do that, I'm going to resolve up the way. So this will give me that mu r is equal to, and then what's pulling it down? Well, it's a 10g force, but it's an angle of 70. We go through the 70 to get to the horizontal. This is 10g cos 70. Unfortunately though, I don't know either mu or r. I know I'm trying to get mu, so we know that mu is 10g cos 70 divided by r. But that doesn't give us mu because we don't know r. So in order to get r, we're going to have to resolve up the way. The direction of r, remember it's a slope, so we always resolve parallel to the slope and perpendicular to the slope. So r is equal to, and we can see it's 10g again, and we go away from the 70, so it's sine 70. So if we take this, we'll get that mu is 10g cos 70 over 10g sine 70, which obviously they're just all numbers, so we can put them into the calculator. But the more savvy of you watching this might realise that the 10s are going to cancel, the g's are going to cancel, and you're left with cos 70 over sine 70, which very excitingly is cot 70. Right, to go back to our trig. So that's 1 over tan 70. So there's quite a nice little result there, right, that you'll get. So mu is equal to cot 70, which is 1 over tan 70, which is 0.364 to 3 significant figures. Bear in mind, if you put 10g cos 70 divided by 10g sin 70, you get the same answer. You don't need to do this cot 70 part. That's just a nice little thing to observe about this situation. It then says for part B that the horizontal force of magnitude P is applied to the box. Given it remains in equilibrium, find the maximum possible value of P. Okay, I'm going to draw exactly the same diagram, but things are going to be slightly different. 20, 10, 10g, r, and then we've got this force coming in at the horizontal, which we're calling P. So we've popped in these forces, 70, and then we know from the first bit that mu is 0.364, right, to 3 significant figures. Now, that's not going to change. So mu is defined by the relationship between the surface and the object, essentially how rough it is, right? So if they were both really well lubricated and this was, say, an icy surface, then the value of mu is very low, whereas if they're both very rough and sort of stick onto each other, then this would be very, very high. That's what mu is. So once you've found mu in this first bit, it's not going to change for the second bit. What is going to change, though, is actually the direction of friction. Right? Think about this. We're trying to maximise P. So P will be at its maximum when this is on the edge of moving up the slope. right? If it was on the edge of moving down the slope, that would mean that P was quite the pathetic force, right? Because it would just be holding it up. But we can still not have this move by P going through and increasing its force so that it doesn't just support the box, but it's right on the edge of pushing it up the slope. So our frictional force, sorry, let me just fill in this 20 here, right, from the Z angle. So our frictional force must be resisting that motion and pulling it back down the slope. Right, it's not the easiest for me to draw because I've already got a force here, so I'm actually going to draw the friction just on the other side, right? And this is going to be mu r here, pushing it back down. So P is trying to move it up and mu r is limited, but this time in the opposite direction. So here we were on the point of slipping down the slope, we're about to move down the slope, whereas here we're on the point of moving up the slope. And in that case, friction will change direction. Friction will always oppose the motion of which you're trying to move it. So again, we can resolve up and we can resolve down. So let's start by resolving perpendicular to get our R value. So we've got that R is the only force supporting it, P is pushing it down into the slope, and this is obviously pushing it down as well. So this is P lots of sine 20 going away to get to that perpendicular angle, and again we're going away here, so it's plus 10g sine 70. Right, then we can resolve it going up the slope. So the force pushing it up is P, but P is resolved at 20 degrees, so to get it onto the slope we have to go through the 20, so it's P cos 20 equals, and then we've got this pulling it down, so this is 10g cos 70, because it's pulling it down, we're going through the 70 to get to the line of the slope, and we've got friction of course on that side opposing the movement up the slope. So this is mu r, so this is 0.364 multiplied by what I've got here, P sine 20 plus 10g sine 70. Right, what a horrendously ugly equation. So I've got only one unknown, but I've got it twice, I've got two p's. So again, what I'm going to have to do is I'm going to have to put those p's on the same side, factorise and divide. So I expand this bracket and I'll move it over. So this is P cos 20 minus, expand this and move it over, 0.364 P sine 20 is equal to 10g cos 70, and of course a 0.364 will have multiplied that. Oh, and there's a 10 there as well, so I'll times 0.364 by the 10, so it's 3.64 g sine 70. Of course this side is now just a number, right, which we can calculate, but I won't do that till the end, right? I don't really see any help in doing it earlier. I'll just get some long decimals that I don't really want to have to deal with. Factorise a p out. And to get my final answer, I'm going to divide by that. So 10g cos 70 plus 3.64 g sine 70 all over cos 20 minus 0.364 sine 20. Okay, so we're getting some quite finicky algebra. If you feel more comfortable, you could work out values of all of this. You'd have to be very careful with your decimals. Make sure you use a high level of accuracy to not affect your final answer. So I've got, type all this in. I'll do the top of the fraction first. Okay, once I've got an answer for the top of the fraction, I'll divide it by the bottom of the fraction, which I'll carefully place within a bracket to make sure it does the subtraction first. Okay, so I get P is equal to 82.2 newtons, right, which is the maximum possible value of P. So that'll be when the object is on the point of moving up the slope, but friction is just about managing to stop it moving. If I increased P a tiny bit more to 82.3, we would see an acceleration start to begin up the slope because friction would be overpowered. Alright, so again, this is going to be exercise 7C. Some of these are getting very tricky now. They're very exam style questions. There's lots of good ones to do. So I recommend that you work through those, doing the odds. And of course, if you want more practice, you can do some of the evens as well.